Okay, good afternoon, everyone. Can you hear me?
Yep.
Okay, all right, thank you. So first, thank you guys for submitting the project proposal on time. So I will go over your proposals and give you some feedback during the weekend, okay? And if you have any questions, you can go to my office hours and we can, discuss some of the details if you have any questions, okay? And one more thing about the final project. So along the development of the algorithm, you can always make some changes, right? Maybe in the proposal, you just give some overall plan, right? But during the course of algorithm development, if you encounter some of the difficulty or some of the like unexpected issues, you can deviate a little bit. So that's totally fine. Okay. Okay, so for today's lecture, we'll talk about adversarial robustness in deep learning or machine learning in general. So we've witnessed a lot of success for machine learning or in deep learning in particular, right? So we see a lot of success stories. For example, image classification, right? So for ImageNet benchmark data set, we are constantly improving the result by developing new deep learning architectures or other techniques. And also, stories about, machine algorithm is able to beat human level intelligence, right, in certain applications. For example, the AlphaGo, right, is able to beat the human in Go game. And also OpenAI has developed the algorithm that is able to beat the human team on Dota games. Okay. So with all these glaring success, right? So the question we want to ask is machine learning algorithm, all these advancement that is truly, ready for the real world deployment, right? So are we able to deploy these machine learning algorithms on real world environment? So the training paradigm of any the supervised method is you have to have a training data set, right? So these can be in the lab controlled environment, right? You collect the data and you ask human labelers to annotate these data to get the labels, and you train your algorithm on these labeled data set, and then you deploy the model on some of the unseen data or testing data, right? But oftentimes the training data is kind of where, curated. And in the real world deployment, because of the, adverse environment, the data distribution is more complicated or not exactly the same as the distribution of your training data. Okay, so if your model is able to achieve very good training accuracy, but during the real world deployment, because of this adverse environment, right, the distribution can be very different than the training data, then your machine learning model may be very vulnerable or brittle to some of the maybe anomaly or other data, which hasn't been, or maybe a little bit different than the training data. So, and the second is the machine learning model can be brittle, based on some of the malicious attack. So these kind of attacks are generated by human, right? So here I'll show a couple of examples. So these are all physical world attacks, right? So for example, if you look at this figure here, if this person wear this particular glass, right? So with these kind of color patterns, and the machine learning model will misclassify this person to this lady. Okay, so here are other couple of examples. Okay, so on the right side, right, so if you see this turtle, there are some color patterns on the shell, right? So a well-trained machine learning model is going to make some mistakes, right? In this case, it is classified as a rifle with much higher probability. Okay, so these are some of the man-made malicious attacks and make this machine learning model break. So the adversarial machine learning, so it's a technique that is attempt to fold the models with some deceptive data, right? So basically, you can add in some perturbations, right? Maybe a small noise to generate this kind of adversarial examples, right? Most of the cases, it will not be perceived by human eyes, right? If you compare these two examples, you may think they are exactly the same, right? There's no difference. But because of this kind of unperceivable noise or perturbation, and they will make the deep learning model fail, right? So for human, we are still able to make the correct prediction, but for the deep learning models, it will misclassify as a bookcase for this particular example. So why this adversarial example exists, right? So if we look at these, any of the classification model, right? So let's just using classification as a simple example, right? So we train the model, then we come up with a decision boundary, right? So to separate, for this case, we have two classes. Okay, if you notice, there's a couple of examples that may lie very close to the decision boundary, right? So if we add in some perturbation, it is likely that this particular data point, right, this red one, adding some perturbations, then it may jump or maybe cross this boundary towards the other side, right? This will be misclassified. Okay, so so if you're interested or know more, how this adversarial example is being generated, there's although it's not there's not no like standard theory, but there are some papers present some of the evidence or reasoning. And one particular example of the paper is here. Adversarial example are not bugs, they are features. So they are kind of analyzed in terms of the robustness of the feature. So you can read this reference. And we can generate, adversarial examples fairly easily, right? For this one, here are some of the examples that can fool a classifier, right? So if you look at a couple of examples here, this baseball, right? If I have this kind of patterns, then the machine learning algorithm will give a high confidence this is a baseball, right? And this one, it will classify this is a remote control, right? This is, we can understand why machine learning algorithm making such decision, right? Because, these patterns are kind of like the prominent features of a baseball, or here, right? This resembles a button, right? This will make the machine learning algorithm to make such prediction. But for human, right, we can easily detect these kind of examples, right? We will not say this is a baseball, right? We will not say this is a remote control. Definitely, we will not say this is a penguin, right? Although they have this kind of gray or black stripe, but we'll definitely classify this as a penguin, okay? And also there's cases, right? These adversarial examples can also deceive human eyes, okay? So the idea is that, have an original image, then adding a very small amount of noise or perturbation. So the resulting image, right, which looks like this, for a human eye, right, we cannot tell like what exactly the difference between the original input and this, perturbed image, right? They look identical, right? Because of this small amount of perturbation. But for machine learning or machine learning system, these small perturbations make a big difference in terms of the classification result, right? So before, right, the original image, it is able to classify this as a panda, right, with 84% confidence. This is a panda. But because of this small perturbation, and it will totally classify it as a different category. And there's also, we can do this in the physical world, right? Not just digitally, right? We adding some noise to the digital image, right? We can also do this kind of adversarial perturbation on the object in the physical world, right? So here is an example, right? So this is a stop sign, maybe in the city of Vancouver, right? So this is the actual stop sign in the city. And people can make some graffitis, right, using some paint, to maybe block some of the region or adding some stickers, specially designed stickers with some patterns, right? Then, if you have a, self-driving car, right, you have the machine learning algorithm to do object detection. So in the machine learning, it will recognize this is not a stop sign anymore, right? It maybe become like a speed limit, or maybe a turn, a left or right turn sign. Okay, so you can see this is problematic, right? If we generate so many of this kind of adversarial attack on these physical objects, then there's going to be a lot of accident, this for this self-driving car if we misclassify the signs. Okay, and also for medical, for medicine or healthcare applications, right? So for this particular paper, they are trying to temper the 3D medical scans, right? These CT scans of the lung, right? They are able to remove or injecting non-existing medical conditions. So this will make the false diagnosis and leading to some false treatment for the patient. Okay, so they also create examples. So here we can look at it. So this is on the left is the original CT scan of the lung. So they were able to injecting a solid pulmonary nodule. Okay, not just injecting something does not exist in the original scan, but also removing some of the cancerous, regions in the original CT scan, right? So this will lead, misdiagnosis, false diagnosis. Okay, there's a. Yes, so that's, yeah, I'm sure you've heard some of the Tesla autopilot fail case, right? One could be because of these adverse environment, right? So you have these, maybe the car is driving in the night condition, right? Some of the maybe the landmarks is not due to the darkness, right? Is not able to, be perceived by the sensors, right? You make the misclassification or detection, right? The other case is you can, do this kind of adversarial attack, right? So adding those kind of malicious attack or patterns, then you can make the machine learning algorithm in this autonomous driving system fail. Okay. So not just attacking the classification task, right? We can actually, attack other tasks like semantic segmentation and object detection, right? So for this example, this is the original image, and this is the perturbation or noise add to the original image. And once we add this noise, and you can see that, right? So the segmentation label are totally changed, right? So before, this is the correct label as, segment, this is a dog, pixel corresponding to the dog class, but after this perturbation, and this will misclassify into a different class. Okay, so for object detection as well, right? So before, we are able to accurately detect this is a dog with high confidence, these three dog instance, but by adding this adversarial noise, and this one was detect as or classify as, I think it's train, and this is a cow, and this is a person. Not just image, right? We can also do adversarial attack on other, modalities, right? For example, for the speech, right? We can add in some of the perturbations, and when you do the speech recognition, and it will totally detect as a different sentence. Okay, and also we can do natural language attack piece and natural language processing model as well. Okay, so next we're gonna talk about how we can perform this kind of adversarial attack. Right, so we know we have a network, right? Let's consider image classification as an example, right? So we have a deep learning network that is trained for image classification. And if we have this original image, right, which is a cat, right, it is able to predict this input correctly. This is a tiger cat. And we can view this input as a vector, right? So if we vectorize this image, we can have a giant vector here. And we can add in some of the noise, right? This delta xi, x2. So that's some small changes to each of the pixels of the original image. And we generate a tagged or perturbate image, right? So in the adversarial attack cases, so the image wouldn't be look like this, right? Here I just make it to say this is attack image, right? So we have a lot of noise, but in reality, the small perturbation adding to the original image, you wouldn't see any difference as compared to the original one. So with this attack image, if we feed that into the same network, same trainer network, right, and you will classify something else. It's not a tiger cat anymore. Okay, so it's something, some other labels, fish or dog, etc. So for the non-targeted attack, right, it will just classify anything other than cat, right? So because you don't have any specific target, right? I just want the network to make a prediction that is not a cat, right? But if you have a specific target, say I want the network to misclassify this input into a particular class, say starfish. So that's the targeted attack. And starfish, this label or category is your target, right? You want the network to predict this particular image, cat image, as a starfish, label or class. So that's the targeted attack. Obviously, targeted attack will be more challenging than non-targeted attack, right? So because we wanted the classifier to specifically categorize your input to a target class. So here are the example of the attack, right? So you have a benign image, which is considered the original one. The network is able to classify correctly. Right here, let's say your network is a ResNet 50, right? And it give you a prediction. This is a tiger cat with 64% confidence. Okay, so that's the probability. And if I'm going to perform a target attack and say the target is starfish, right? I'm adding some of the perturbation, and this is the attacked image. And the same model, right? The network ResNet 50, it will surprisingly give you a 100% this image is a starfish, right? So the network say, I'm 100% confident this is a starfish, which is very striking, right? Why this is a, to a human eye, right? We definitely will not classify this as a starfish. And you may think maybe the model think there's the ear maybe looks like the starfish shape, right? But if we want to do, we can also do some other noise and make a different label, okay? And if we look at the benign image and the attack image, right, we do the subtraction, and we also magnify the difference between these two images by 50 times, and we do see there's some difference, right? So these are the differences between these two images. So we can also, make the network to predict the target as a keyboard. Okay, so here the network is to make a prediction. This input is a keyboard with 98% of confidence. So, and you may think, is this because of the network is not trained properly? So, the network is making this kind of false prediction. It's actually not, right? So this network is, first is ResNet 50. So it has a very strong representation capability. And second of all, it is well trained on the ImageNet, right? If we just randomly adding some Gaussian noise, right? It's not like a specially designed perturbation. We just randomly add some Gaussian noise, right? You can obviously observe the noise add to the original image, right? The network is still able to predict this is a type of cat, but not the same subcategory, but still it is able to recognize this as a cat, right? If we further add a more severe Gaussian noise, right, you can see the noise level is increased, right? The network is still able to recognize this is a Persian cat, right? Maybe because more noise, the network think the cat is more fluffy, right? To make this kind of prediction. Even we adding further more noise to the image, right? And the model classified this is the fire screen. And we can understand why the network makes such prediction, right? The fire screen, maybe it the network think maybe the noise is the screen, right? The foreground, which is the cat, you had the shape and the color look like a flame, right? So it'll recognize this is a fire screen. So basically, what I mean here is that the network is not poorly trained. It is well trained, right? It's able to recognize these random added Gaussian noise. But for some of the specially designed, perturbations, it kind of totally failed, right? Make a wrong prediction with high confidence. So how do we, adding these kind of perturbations to the original image to make the model, a trained model fail, right? So consider we have the original image, right? Let's still take this cat as an example, right? We have a trained network F, and X0 is the input, and the network is able to make a correct prediction, right? This is the class distribution, and the cat has the highest score. And if we want to perform the non-target attack, right? So we want to, adding some perturbation and generate a new image, X, right? If we have this new image feed into the network, and it will generate output, Y. And we want this prediction as far away from the ground truth, Y hat, which is cat, right? In terms of one hot encoding. So that's the non-target attack, right? We just want the prediction that is far away from the cat, right? Any class but cat, okay? So we can formulate object function, objective function, right? So we can come up with a loss function. So here, E, Y hat, we can using this cross entropy, right? So in the normal supervised training, if you want to train a classifier using the original image, right? We using the cross entropy as the loss function, and we minimize this loss function, right? To make sure your prediction is as close as possible to the ground truth label, right? But in the adversarial attack case, right, we want your prediction, far away from the ground truth Y hat, right? So now we want to maximize this cross entropy, right? And if we still want to using minimization, then we adding a negative sign before it, right? So we minimize the negative cross entropy here. But for the targeted case, we have to adding one additional constraint, right? As compared to non-targeted, we just want the prediction far away from the ground truth, right? But for the targeted attack, we also want your prediction as close to the target I given to you, okay? So far away from the ground truth, at the same time, that is close to the target label, Y target, okay? So say if you want your target is fish, right? Then I want my fish, the score for the fish go higher, right? So in terms of the objective, right, we have to add an additional term, right? This cross entropy of your prediction and this target label, right? We want to minimize that as well, okay? So does this mean everything is settled, right? We can take this objective function and optimize the network to generate this image. We actually have one more constraint, right? That is, we want the generated image, right? This new image, perturbed image, as close as possible to the original one, x0, right? Maybe that is not able to perceive by human eyes, right? So that will translate to a constraint. So we can, using some measure, right? We can compute the distance of the original one, x0, and the perturbed image x, right? We add a constraint, right? This distance should be smaller than certain threshold epsilon, okay? And this difference should not perceived by humans, okay? Right, so like you cannot notice there's any noise has been added to the original image, okay? So that's the overall optimization if you want to perform adversarial attack. Here we can discuss a little bit more on this, non-perceivable by humans, right? So how to getting this kind of constraint, right? So we have a distance, right? Obviously, there's many ways to measure the distance between your original image and this kind of attacked image, X, right? So there's some common ones we can use. First is we can, using L2 norm to measure the difference, right? So basically, you have this original input at X0, and this is your attacked image or perturbed image, X, right? So this is the difference. So you can compute the square of all these elements, or you can do you can also do the square root. So that's you can using L2 norm to measure, and also you can using the L infinity to measure the difference. Okay, so for the L infinity, basically you just compute the absolute difference for each of the element of these two images. Just for every pixel, you compute the absolute difference, and you find which one is the maximum, and using that as the distance to measure. Okay. So let's look at an example, and which one may make more sense, right? If we want to not perceived by a human. So let's consider this a very simple example, right? Maybe you have an image, only have 4 pixels. Okay, I'm using different colors to indicating different pixel values. You can change every pixel a little bit, right? Maybe resulting image like this, or you can change one pixel a lot, right? In this case, if you notice, I make a large change on this green pixel, right? So here, the resulting image here has a dark green, okay? But for the first case, every pixel is changed a little bit, but you didn't see much of a changes, right? In terms of a color and a contrast. And if we compute the L2 norm, these two cases can essentially have the same L2 norm. For example, for the first case, I change maybe 1/2 for each of the pixel, right? Maybe adding 1/2 to each of the pixel, right? So you compute L2, right? How much you get, right? 1/4, 1/4, 1/4. A quarter, you get a total of 1, right? On the second case, I can change the screen pixel like 1, 1, right? If you compute the L2 norm, right, they are basically the same, okay? But if we compute the L infinity, right, so here the L infinity is 1/2, right, because we change every pixel by 1/2. And for the second case, right, we change this green pixel by 1, so the L infinity is 1. So definitely the second case here has a larger L infinity, right? So that means, the human eyes may be more, sensitive to a large change of the pixel. That may cause some of the contrast to change rather than you change a little bit on a lot of pixels, right? Maybe that wouldn't change a lot of the contrast. And also this L infinity is a more like a sensitive like detector, right? To tell how much of a changes it are made, right? So in this case, if we consider the human perception, maybe the L infinity is a good measure to measure the difference between the original image and the perturbed image, okay? So that's the optimization, how we can generate a tagged image, right? So if we don't consider this constraint, right? If we just forget about the, small perturbation, this constraint, we just, consider minimize this loss, right? If we compare with this normal, network training, right? So we, in this, we train the deep learning network, we have this optimization function, right? And the goal is to, to do this gradient descent and update these parameter, right? But for this case, because the network is fixed, right? We assuming we are using the same network, so the model parameter is fixed, okay? But there's nothing, there's not much difference, so essentially. So in this case, we are not changing the parameter, but here we are actually changing the input, right? So you can consider this is like an additional layer of the network, right? So you can, using the same method to do this kind of update to minimize this loss function, okay? So to do so, we can, again, using this gradient descent, right? So we can start from the original image, right? The reason we start from the original image is the perturbed image will be very close to the original one, right? You don't want to start with a random image, right? You can just start with the original one, then make some changes, small changes, so that you can alter the model's decision or prediction, okay? So we start from the original image x0, and we also do this iteratively, right? So we can do, a total of t iterations. So for each of the iterations, we can compute the gradient with respect to each of the pixels, right? Remember, now we are not updating the model parameters, right? We are update the input, right? So each of the pixel values here. So we can compute the gradient for each of the pixel, and we can have a learning rate. And so this is the standard gradient descent, right? How you update for each of the step. So that one is we don't consider of this constraint, right? So we can do this gradient. And if we want to consider this constraint, right, we want to make sure, the generate image is very close to the original one. So how do we incorporate this constraint in this optimization? It's actually very simple. So if we want to consider this constraint, right, and for this particular update, right, if you can measure, right, if this, the difference between the update, right, the t's update and the original one, is it greater than the threshold? If not, right, nothing will happen, right? You can, go to the next iteration and do this update. And if the distance, right, is greater than the threshold, you set this epsilon here, and we can, using some of the method, trying to kind of pull your change, back to within the boundary. Okay, so let's say if we consider, consider this L infinity, right, as your measurement. Okay, so basically you can find out, right, what's the boundary, how much change you can do for this original image, right? So if for some of the, for the step, right, after the update, the image is kind of exceed out of this boundary, then you can pull this image to the point that is close or just reside on this boundary. Okay, so just like you do, gradient descent, right? The optimization, like a gradient clip thing, right? You have a large gradient, right? You set a threshold to clip that gradient. So this is essentially the same thing, right? You can fix that to make sure that the difference is smaller than the threshold you set. So other different attack approach, they may have different constraint, right? So they may have more complicated constraint, and also they may have different optimization methods. So for the next one, we're gonna look at one simple attack approach that is called fast gradient sign method. Okay, so here I list the paper. So if you're interested, you can read the paper to understand some of the more details in the paper. Okay, but the basic idea is still we have this optimization function here. Okay, we also have the constraint, right? You have to less than this threshold. And for this fast gradient sign method, or FGSM, instead of doing this optimization for a couple of iterations, it aims to do a fast step, just a single step, right? Instead of doing T-step, I'm going to just do one step and trying to create a perturbed image that maybe can make your model fail. Okay. So that's one one change for this FGSM. Just do one step. And the second change is that not in the gradient update step, not just take the original gradient value. It considered the sign of the gradient. Okay, so you can see there's a function, this sign function here. So what it says is if whatever the value here, right, is greater than 0, you are going to generate a sign of +1. Okay, otherwise, I'm going to output a sign of -1. Okay, so basically, instead of the actual gradient value, it will just output the signs of the gradient. Okay, either +1 or -1. Okay. And also for the learning rate, we will set as the threshold epsilon here. So basically, this is trying to make sure if you're using this L infinity as the measurement of the difference, you will make sure that you are under this threshold. Okay. So FGSM is not targeted like you want to achieve a very high successful rate for the attack, but it's more targeted on a quick way to do this kind of attack, right? You just do this one time. On the later work, this iterative FGSM, you can do maybe not necessarily limiting just to a single step. You can do this iteratively, right? You can do multiple steps, maybe 5 or 10 steps to improve the performance or attacking success rate. Okay, so again, if for some of the iteration steps, if the difference is greater than the threshold you set, then we can using the same strategy, right, to pull the uptake back to within the boundary. Okay. So in the previous example, we talked about this is called white box attack, right? So essentially, we know the network parameters, right? So we know the network architecture and we know the parameters, right? So then we can, compute the loss, right, and do the backpropagation to update the input, right, to generate a successful attack, right? So this is the white box attack. So basically, you know everything, right? What's on the hood, or what's the beneath the model. But in a lot of real world applications, right? Maybe you have a online API, right? The provider, does not release the model parameters, right, to the public, right? Most likely, they will just host the model in-house, right? You can only maybe submit your query and the server give you the result, right? But they won't release or review the underlying models, okay? So does this mean, we are safe? We are not, if we don't release the model, right? We are not under, attack, right? If we are just, consider white box attack, right? If the attacker doesn't know what kind of model I'm using, does that mean I'm safe, right? I have no risk of being attacked. The answer is no, right? Because there's another category called black box attack, and it is possible. So the black box attack means we don't know the model, the parameters and of the model, but we are still able to generate, adversarial examples to make the model fail. Okay. So how do we do the black box attack, right? So let's say we have a network which is black box, right? We don't know the network architecture, network models, parameters. But if you do have access, to the training data of this network, right? Let's say what kind of training data this network is being trained, and you can actually create a proxy network, right? So in other words, you can create a surrogate network, right? Maybe not necessarily exactly the same as the target network because you don't know what that is, right? But you can create a proxy network freely by yourself, right? Maybe let's say the target network, maybe ResNet 101, okay? But you don't know that. But maybe based on experience, you can say, I'm going to create like a ResNet 15 or ResNet 18. So this is your proxy network. Then, you can, and you also have the access to the training data, right? So then you can, using this proxy network to generate attacked objects, okay? So basically you're using this self-created proxy network, right? And trying to create attacked object, right? So you take all these examples, right? Trying to generate perturbations for all, each of these images, right? Generate a perturbate or attacked images to make your proxy network fail, okay? And then hopefully the attacked object or attacked images is also can make the target network fail, right? So, which means the attack images has some transfer ability, right? It makes your proxy network fail. Maybe it will also make the target network fail, okay? But what if you don't have the training data, right? So this is the case for a lot of like online service, right? You don't know how their machine learning model or engine is being trained, right? You don't have any access to their training data. Then how do we do this kind of black box attack without knowing the model parameters, without knowing the training data? So there's actually a way to do so. Basically, you can, maybe upload some of the image you have, right? You can, collect a couple of images by yourself, right? You can upload these images to those online services. Let's say the service is an image classification model, right? You can upload those images to that service, and that service will generate a label, right? It will generate prediction for your uploaded data, right? You can do this many as you want, right? Maybe 1,000, 10,000 times. So in this kind of query-based scenarios, you can generate an image and a label pair, right? Like 1,000 pairs, right? And then you have the data, right? You can train this kind of proxy network using the data and the corresponding label generated, and generate this attack image, and using that to attack the target network, okay? So basically the underlying principle for this black box attack is based on the transferability, right? So assuming you learn some adversary based on the proxy model, which is white box, right? Because that's the model is you created. You definitely know the model parameters, right? You can using that to generate adversarial examples, and hopefully this adversarial example is also able to transfer to the black box system that can also make this these system fail. And to increase or improve the transferability, right? You are not limited just to train one proxy network, right? You can essentially create multiple white box proxy network, right? You have multiple white box models, and you consider that's like an ensemble, okay? You want to create adversarial examples that that are successful on all these models, right? So that kind of intuitively makes sense, right? If your adversarial example can make a range of white box models fail, then the transferability will be much improved as if you just train one white box model, right? So then you can take these adversarial examples and apply it to this black box system, right? So most likely, these adversarial example will also make this kind of black box system fail. Okay. And here are some of the experiment result this paper has produced. So this is the black box attack. Okay, so for this table, on the first column, right? So this is the proxy network, and the first row is the network to be attacked. So so if we just look at the first one, right? So the proxy is ResNet 152, okay? And the target model to be attacked, the first one is ResNet 152. In this case, this is a white box attack, right? So the same network. So as you can see that you can easily achieve, make the network have the 0% accuracy, right? So which means you have 100% successful rate, okay? You make the network to fail all these examples. Okay, if we go to still take the ResNet 152 as proxy network, right? The target network is ResNet 101, right? As you can see that the classification accuracy is 13%, right? Again, this is, I can say this is a high successful rate, right? Because you only make this ResNet 101 achieve 13% accuracy. Okay, obviously the lower accuracy you can make it, then the more successful attack you can achieve, right? So here, the attack to the target network is ResNet 50, and the proxy network make this ResNet 50 only achieve 18% accuracy. Okay, so here the second row is you switch another proxy network, right? So ResNet 101, and this is the target network, and ResNet 101, right? Basically on the diagonal, this is white box attack, right? As you can see, that white box attack definitely has higher successful rate as compared to the black box, right? Because on the diagonal, you are able to achieve 100% successful rate. Okay. The second table here is the ensemble attack, right? So on the upper table, this is just train one proxy network. Okay, so any of these 5 network is, you can choose one of them as your proxy network to perform this attack. And you can also choose a committee or maybe a multiple networks, right, as your committee, and trying to generate those adversarial examples and to perform the black box attack. Okay, so on the first column here, this has slight interpretation as the first table here. So you see there's a minus sign here, basically means out of these 5 networks, right? ResNet 152, ResNet 101, ResNet 50, BGG 16, and GoogleNet. I'm going to remove this ResNet 152. Okay, basically just considering the remaining 4 networks as your ensemble and train adversarial examples and trying to do black box attack on all these networks. Right, as you can see that, right, so it is performed quite well, right? So have this classification accuracy 0%. And so this one means out of these 5 networks, remove ResNet 101 as the ensemble and do the adversarial attack on the rest, okay? So before we see that black box attack is possible, right, and is able to achieve very high successful rate. But one downside is that for these attack is for each of the image, you create some of the perturbation, right, and then adding those perturbation to the image and trying to fool the fool your original classifier or machine learning model. Okay. So each individual image, you will generate a different perturbation or generate a then resulting attack image to make the model fail. But is it possible that we can generate a single perturbation signal and apply this perturbation to all the images you have, and so that the model can fail on all these images within this kind of perturbation? Right, so this is called universal adversarial attack, right? Basically, you have a single perturbation signal or vector, right? Any image, original image, and add these perturbation, and you will generate this kind of attack image can make the model fail. And this paper shows that this universal adversarial attack is also achievable, right? So basically, this is image agnostic, perturbation that can make all many natural images to misclassify with high probability. Okay. So all the previous discussion, that is basically we are adding these kind of perturbations on the digital image, right? So can we do adversarial attack in the physical world, right? That means can we, actually generate some of the actual object, right? For example, this glass, right, or this sunglass. And if a person wear this sunglass, right, then it will misclassify to a different identity, right? So in this case, this man wear this specific designed glass, right, with this pattern, right, he will be misclassified as this lady. Okay, so this is the physical world attack, right? We are creating something physical, right? So when, attach this kind of physical attack patterns, then your machine learning model will fail. So for the physical attacker has to find a perturbation, that can generate beyond a single image, right? So you cannot just, generate perturbation that work on one single image, right? Maybe you want to have this kind of glass, right? Anyone wear this will misclassify it to a different person, right? So this is kind of universal attack, right? Also, you want to craft perturbation that may not be compromised by the printer, okay? Because some of the if you generate this kind of pattern, right, you have to print it, right? And digitally, if it working digitally, it may not necessarily working in the physical world, because the physical printer, when they print these colors, there's some of the nuance difference, right? Because the printer can print so a limited number of color levels. So you also want to make sure this kind of, after doing this kind of printing, it is also going to be working, right? It's able to make the machine learning model fail. So this is a physical world attack examples. So in this paper, they were doing two kinds of physical attack. So the first two columns, they are printing a poster. Okay, so you have this traffic sign poster. Okay, so they're adding some of the perturbations and to the original image and print it out, and ask the machine learning algorithm to to make the prediction, and they are able to achieve very high target attack success rate. Okay, so and the second physical attack is they have the actual stop sign. So they put in this actual stop sign, and they adding some specific patterns, right? So you see here they are using some graffiti to paint some special patterns on this stop sign. Right here, you also doing some camouflage art, right? Like maybe have some stickers here, but they are carefully designed camouflage art or graffitis, right? Not just randomly. So when they attach this kind of camouflage art or graffitis, and the machine learning model will fail, right? So they have a very high successful attack rate on this kind of physical object. And here is also a very concrete example, not just for classification. This is actually doing attack the object detection system. So the author of this paper here, they were doing print out this particular maybe a drawing or painting, and if this painting was held by a person or maybe attached to a body of the person, then the YOLO V2 object detector will fail to detect this is a person. So let's look at their demo video. So as you can see that, right? So this person has this, print out maybe a paint, right? Stick to him, and the YOLO V2 is not able to detect this as a person, right? But for this one, left one, you can see the bounding box of person is constantly appear, right? So when he kind of flip over this, let's say the painting, right? The detector is able to detect this. He's also a person, right? When he flipped over, then the detector fails again. Okay, now he's kind of transferred this painting to the other person. Right now, the object detector is able to successfully detect him as a person, but fail to detect this guy, right? Because he's holding this painting. So as you can see, you can imagine, right? You can actually, print this paint in a t-shirt, right? Just like people wouldn't notice, right? They were just, okay, see, oh, you have a t-shirt, maybe have this kind of drawing or painting. It's a cool painting, right? They wouldn't notice this is actually a adversarial attack, right? People wouldn't notice or even consider this is some malicious attack. They will just think, okay, this is some maybe, this more like some person sitting in front of some store, right? Okay, so this is the physical world attack. So we talk about a lot of attack, right? So definitely we also want to do defense, right? So how can we make the our machine learning model, robust to this kind of attack, right? Because definitely if the machine learning model is not robust to this kind of adversarial attack, that can cause some of the catastrophic disaster, right? Like the medicine or the healthcare domain. So we have, can categorize these defense mechanism as passive defense and proactive defense. So for the passive defense, right? So we have this, original image, then we add this attack signal, and we want to build some, kind of filtering mechanism. Hopefully, can filter out this kind of added attack noise or signal, right? So once we apply some sort of filter, right, it won't affect the classification, right? So maybe after the filtering, the attack signal become less severe, right? Maybe less harmful, and the network is still able to recognize its original label, which is a cat, rather than if you don't do any of the filtering, it will misclassify this as a keyboard. Okay. So you can immediately think, right, filtering, how can we do the filtering, right? We can do, the simple one is we can do smoothing, right? We can using some image pre-processing, right? Apply some Gaussian blur, right? A Gaussian kernel trying to smooth image, right? So hopefully, during this kind of smooth processing, right, the added attack signal or noise can also be smoothed out, right? So the attack effect will be not that severe. Okay. So here, after smoothing, right, so the original image with the attack signal, the model is classified as a keyboard, right, with a high confidence. If you apply some smoothing, right, and I think the smoothing effect is noticeable, right? If you look at this, the face region, the eyes, right, the edge kind of smooth out, right? Look a little blur as compared to the original image, which has very sharp edges, right? With this smoothing effect, and the model is able to predict a cat, right? Although the confidence is not very high, but at least still able to predict this is a cat, okay? But there's also some side effect, right? For some of the image, right, if the model is able to predict correctly, this is a cat, if you apply further smoothing, right, you miss some of the, or destroy some of the sharp edges, then you can also, kind of decrease the confidence of the model prediction, right? So now the model only have 45% confidence this is a tiger cat, right? So that's some of the side effect, right? Because of this smoothing effect, you lose some of the high frequency component or information in the image. There's also other techniques, right? Using this kind of filtering technique, right? The other one here is image compression, right? You can using some of compression algorithm like JPEG or JPEG 2000, right, to compress the original input, right? And after you do the compression, and the compression algorithm will introduce some of the artifact, right? For example, you can see this kind of JPEG compression, they will introduce some blocking artifacts or blurring, right? So again, the idea is hopefully this kind of image distortion will also kind of distort the signal, right? So that the model, can still make the correct prediction. It's not influenced by the attack signal. Okay, so that's image compression. And also, we can using GAN, right? We can using train a generator to train, to generate, not take the original input, but generate an image which, resemble the original input, but hopefully during the image generation process, right, some of the attack signal or noise can be removed, right? We can train a conditional GAN, right? Using this as a condition to output a similar or the same image, right? You can tell there's some difference, right? Maybe there's some color differences as compared to the original input, right? Hopefully this image generation process can also filter out some of the attack signal, so your model wouldn't be affected by these perturbed signals or noise. And we can also do some randomization to improve the robustness to the attack, right? So for the original input, we can have resize, crop out some of the region, right? And and also pad some of the cropped region, and so you generate this kind of randomly padded image, right? So some of this kind of randomness can also improve the robustness to some of the adversarial attack. So that's the passive defense. So for the proactive defense, we'll actually, including some generate some adversarial example during the and for the training. Okay. So basically, you are given a training set, right? So you have the image X, right? You have n training images, and you have the corresponding label, right? Y hat 1 to Y hat n. So typically, the normal training is given this training set, right? You are using that to train your model, right? But to perform this adversarial training, and for these n samples, you want to try to find adversarial input given this original one. You can, using some of the attack algorithm, right, trying to generate the adversarial examples. Okay, so this is X tilde n. That's your adversarial example generated based on xn, right? So you can, for each of the image, right, x1 to xn, you can generate its corresponding adversarial examples. Okay. So you basically double the training size, right? In addition to your original image, and you also have the adversarial example for each of the training data. But because right, this adversarial example is you generated, you actually know the ground truth label, right? So you actually apply or append the ground truth label to this adversarial example, okay? And you use the original one and the adversarial examples to train your model, okay? So the intuition is that, right, during the training process, your model see the original benign images, but at the same time, your model also see adversarial examples, right? But we are forcing, the ground truth label to this adversarial examples. So this will make the model to learn, okay, this adversarial example still has the ground truth, the correct label, right? So they learn to know or to aware to detect what kind of signal is this kind of attack signal. So once your model is trained this way, then if you have a adversarial example during the testing, then because we already see this kind of example, right? So the model will most likely able to recognize that and still able to predict the correct label, okay? So you can consider this adversarial training is a way of doing data augmentation, right? So as compared to the classic data augmentation doing like cropping, rotation, in this case, we are generating adversarial examples as your data augmentation, right? Trying to improve the robustness to adversarial attack. Okay. So here we also list some of the attack approach. So if you're interested, you can check all these different approach, and they have different success rate, and they are designed maybe for black box attack, universal adversarial attack. So if you're interested, you can check these list of references. Okay. And also, you can also read this survey paper. So this is very comprehensive survey. Some of the advances in adversarial attack and the defense in computer vision, right? We're not just interested in attacks, we are also interested in defense mechanism, right? How can we build advanced defense mechanism that to improve the robustness of the machine learning model, so that if you deploy in the real world scenarios or applications, you can have a peace of mind. Okay. Okay, so that's it for today. Any questions? Okay, so if we don't have any questions, we're gonna stop here. One quick reminder, so the programming assignment 1 is due February 25th, I believe. So make sure you are working on that and submit the necessary files on time, right? So I believe you have to submit the report and also the code. If you have any questions, let me know so you can we can discuss maybe during the office hours, or you can send me separate emails. Okay.
Yeah, actually, I have one question
Yeah.
regarding the assignment. What level of accuracy should we expect? Just to kind of know, like, if we're really messing up somewhere or not.
So so if you achieve like around 50%, you can definitely say your network has some issues, right? 50% is just like a random guess, right? Because we're doing binary, right? So
True. Okay.
so that's kind of a level of like the lower bound, right? If you are achieve very low, then there's some problem, right? So depending on what kind of network you are using, right? So I recommend you guys using smaller network like ResNet 18 or MobileNet because of the computation resource limitation. Yeah, so I think, but for this one, I think I give you some, did I give you some the reference? You can check like what's their other baselines. So that's another way, right? You can check the data set or any published papers and see what do they achieve, right? You consider that as a baseline. So you don't have to like achieve the state of the art, but at least on par with some of the existing work, right? If you found a paper, or maybe this is a Kaggle data set, right? There's definitely there's like a leaderboard for them to, you can check like what's the top performance. Maybe they achieve like 90% accuracy on this data set. So yeah, maybe that's your target, right? If you achieve like 85, that's reasonable, right? You don't have to be the state of the art, but more or less in that range, not like very low range, like 50%. Then that's just random guess.
Okay. Thank you.
Yeah. Okay. All right. Any other questions? Okay, so if not, we're gonna stop here. Hope everyone have a nice weekend. We'll meet again next Tuesday. Okay. All right. Bye, everyone.